So in question 27, what we've got is a ceiling, and hanging from this ceiling is a spring. And then what somebody does, so yes, initially this spring is just unstrained. It's just hanging there happy. But then somebody comes along and they attaches a block to it. So they stick a block on the end of it. And while they're holding that block there, the spring is still unstrained, so it's happy. But then what they do is they let the block go, and so the block falls, and as it does so, it stretches the spring out. But eventually, the spring has had enough, and it applies a big enough force to bring that block to a momentary halt, at which point it just momentarily stops, and then the spring continues applying its force back upwards, and then it will start accelerating the block back up again. Now we're actually told something about how far that spring gets stretched before it starts buoying back up again, and we're told that it drops 0.15 meters. So let me represent that on here by this. So the distance that it drops is just h, which is 0.15 meters. And we're also told the mass of this block that's sitting on the end of the spring, that's got a mass of 0.45 kilograms. And so from this information, what we want to know is what the spring constant of this spring is. So we don't know that. Now what we can make use of here is the fact that there are two forces doing work on this block. And we also know that in total, the amount of work being done on this block as it goes from here down to here has got to be 0. Because there are two forces, gravity and the spring force acting on it, and yet the block starts from rest, and at the final time that we consider, it's at rest again. So it starts from rest, accelerates down, but then eventually gets decelerated by the spring and comes to a momentary halt. And so in between these two positions here, the change in the block's kinetic energy is 0, and so the net work that gets done on it also has to be 0. So that's probably going to be a handy piece of information. So let's write down that the net work being done on this block is equal to the work that gets done by gravity plus the work that gets done by the spring force. So here is work done by gravity. So the work done on the block by gravity. Work done on block by the spring. And so by the work kinetic energy theorem, since the kinetic energy of the block since the kinetic energy of the block, when it's released and when it comes to a momentary halt, is 0, the net work being done on it is also 0. And so we have that the work being done by gravity plus the work being done by the spring force has got to be equal to 0. Now, what's the work being done by gravity? Well, we know that that's going to be equal to the negative of the change in the block's gravitational potential energy. And the work being done by the spring on the block has got to be equal to the negative of the change in the spring's elastic potential energy. And if we define this down here to be the reference point, so if we say this is 0 meters here, so here is our reference level. That means that the change in the gravitational potential energy is going to be the initial potential energy, the final potential energy, which will just be 0 in this case, minus the initial potential energy, which is going to be mgh, if this is the reference level. And now the change in the elastic potential energy is just going to be the final elastic potential energy minus the initial elastic potential energy. And the final elastic potential energy will just be a half times the spring constant times the amount that the spring has been stretched from its natural length. So in this case, the amount by which it's been stretched is just this h. So the final elastic potential energy is going to be a half k times that h squared. And since in the initial position the spring wasn't stretched at all, the amount of elastic potential energy stored in this system was just 0, and so we take off a 0 there, and that's all got to be equal to 0. So finally, if we do some simplification, expand these brackets out, we have a minus times a minus, which just gives us mgh, and then we have a minus a half k h squared is equal to 0. Now, both these terms here have a factor of h, so if we divide both sides of this equation by h, what we'll find then is we get mg minus a half kh is equal to 0, and since we know what this height is, it's 0.15 meters, we know what the mass of the block was, and we know what g is, we can now go ahead and solve for the spring constant, which is what the question is asking us for. So if we now just add a half kh to both sides of this equation, we get that cancelling out with this on this side, and so we then find that mg will be equal to a half k times h. And now to get h by itself, we just divide both sides of the equation by a half times k, and so we finally end up that h is equal to mg divided by a half times k. Now something divided by a half is just going to be that something multiplied by 2. So another way of writing this would be to say that h, the height, oh dear, I've solved for the wrong thing, haven't I? We don't actually want to know the height, we know that. What I want to know is what the spring constant is. Sorry, just forget that. So now, instead of dividing by a half k, let me divide by a half h. So we're going to get that k is equal to mg divided by a half k. And as I was, sorry, a half h. And as I was just saying, when you have something divided by a half, that's the same thing as a half divide, sorry, that's something divide. When you have something divided by a half, that is the same as that something multiplied by 2. So in this case, we're going to have that the spring constant is twice mg divided by h. And so if we plug these numbers in through the calculator, then we get 2 times the mass, which is 0.45, multiplied by 9.8, and then divided by that height, which is 0.15. And we end up with the spring constant being 58.8 newtons per meter. And the last thing we want to know is what the angular frequency of the block's vibrations are. And so that's just a simple application of a formula that says that the angular frequency is going to be given by the square root of the spring constant divided by the mass of whatever's on the end of the spring. So in this case, that's going to be approximately equal to the spring constant divided by the mass, which was 0.45, or 11.4 radians per second.